This last video of chapter 11, and I guess of your Math 60 career, is on infinite geometric series. So the best way to describe an infinite geometric series is to actually get you to stand up and face a wall. And I know this feels silly. Maybe you can even just move your feet. Maybe you've got your feet I'm moving my feet just towards my desk, right? And if I ask you to half your distance to your desk or to the wall, you move your feet so that they're halfway there. And then if I want you to half that distance again, you're like, okay, no problem. Maybe you started far from a wall and you're getting some exercises and you're getting closer and closer to it. But the whole idea is that you keep having your distance. Right? If I keep having my distance, so maybe I started at a meter and then I half it, now I'm at half a meter, and then now I'm at a half of a half, and now I'm at a half of a half of a half. Technically, will you ever reach the wall? Well, no, because I'm always taking some distance and I'm halving it, and it's not going to be zero. It's going to be theoretically zero, though. Because if you take a number like 1, ooh, I wonder if I can bring up a calculator. Here. Let's go calculator. So let's say that I take a distance like 2 and I divide it by 2, right? And then I divide that by 2. And then I divide that by 2. And I divide by 2, divide by 2, divide by 2, divide by 2. What's happening to my number is it's getting smaller and smaller and smaller until my calculator, because it's just a cheap, there we go. It's going to let me keep doing it, just stalled out. It's going to keep going, but it's never going to be 0. But it's going to be 0.0000000. It's going to be theoretically small enough that you're touching the wall. So the question is, could you find the total distance that you've traveled until you theoretically reach the wall? And why or why not? And so really, if you started 2 meters away from a wall, right? And you half your distance, 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 and you half your distance. Could you find the total distance that you traveled until you reached the wall? Wouldn't it just be 2 meters? Yeah. So yes, you can find the total distance until you theoretically reach the wall. Well, what is the total distance? 2 meters. But let's look at the algebra behind this. We know that this is our equation for finding the sum of any geometric series. Let's put in that r is a half. So let's say Sn equals, doesn't matter how far away you start from the wall, I'm going to say that you're halving your distance. My equation is going to look like this. Now, what's going to happen to this r to the n term as n gets larger and larger and larger? So 1 over 2, squared. Well, that's just a quarter. But what if I put in 1 over 2 to the 100? Well, all of a sudden that's 1 over 2 to the 100. No, I don't know off the top of my head. It's 1 over 1.26 ... times 10 to the 30. It's huge. So even finding the first 100 terms until you theoretically are reaching the wall, right, gives you essentially 0. If I do 1 divided by that answer, I get 7.89 times 10 to the negative 31. I mean, that's 0. Right? So even with an n that's not even that large, right? Like it said, try something that's very large. So even something that's not very large is making this essentially go to 0. So what would you be left with? Well, in my equation, if r to the n is going to 0, I'd be left with a1, so the first term, times 1 minus 0, all over 1 minus r, whatever that r value is. And this one, it's a half, right? But the whole point of this is that the r to the n is going away. So you're left with the first term times 1. So the sum of an infinite number would be the first term divided by 1 minus r. We can actually completely cut out this part of the equation because it's getting closer and closer to 0. Right? So if we said, n is 100, it's pretty much already there, right? It's not going to affect your equation. So this new equation we can use to find the total distance traveled. So in our example, let's say we started with A1 being the distance that you travel, right? So if you're starting 2 meters from a wall, let's make this clear, right? I know I'm going to travel a total distance of 2 meters. But my first amount that I travel is 1 meter because it's half of that distance. And then I'm going to go half of that next 1 meter. So I'm going to travel half a meter. And then I'm going to travel a quarter of a meter, right? So the first term is 1. And my common ratio is a half. Now to solve this, I can do 1 divided by 1 minus a half is a half. And a half goes into 1 2 times. There's my answer, that 2 meters of distance. So we've come up with this new equation that we can use to find the sum of an infinite series, which looks like this. So this is only for geometric series, okay? And also this is only for geometric series where the r value is less than 1. Now the absolute values mean that r has to be less than 1 and r has to be greater than -1. Right? So if you solve an absolute value twice, right? One as is, one flip flip, r has to be between -1 and 1. In other words, r has to be making your sequence smaller. Why? Well, when our r value is a half, our numbers are getting closer to 0, right? And so we can say that there would be an infinite sum because essentially we will reach 0. But if my r value is 2, so this is an r value of a half, if my r value is 2, instead of my sequence getting closer to 0, it's getting further away from 0. And so there's no way that I could find the sum because the numbers can get infinitely large. And so I can't find the sum of an arithmetic or geometric sequence that has an r value that's bigger than 1 or less than -1. All right, so what are we going to do? Well, we're going to use the formula. So here we go. Determine whether each of the following infinite geometric series has a sum, and if a sum exists, find it. So here's my first geometric series. To find the common ratio, you take the second term, you divide it by the first term, and you get a common ratio of 2. This series is getting bigger and bigger and bigger. In other words, sure, you could find the sum of some number of terms, but you can't find the sum of the infinite geometric series because you're not approaching 0. Okay, whereas if you look at this guy, to find the r, we're doing -4/3, the second term, divided by the first term. I'm going to rewrite this as -4/3 divided by 4, which means that I'm doing -4/3 times a quarter, 4 divided by 4, and I end up with -1/3. Okay, since my r value is between -1 and 1, I can find the sum of the infinite series. Starting with the general formula, first term divided by 1 minus r, and then I just plug it in. My first term is 4, and my common ratio is -1/3. Much easier to find the answer for. So I'm going to do 4 divided by, this is 1 plus 1/3. So I'm going to change that to a common denominator of 3, which is going to give me 4 divided by 4/3. And I get 4 times 3/4, which gives me 3. And I know I did the fraction work there and I could have used a calculator, but I just want to show you that sometimes it's worth trying your fractions again, just so you don't lose those skills. All right. And just using the different summation notation, I want you to pause the video and find the sum of this infinite geometric series, if possible. All right, so my equation is the sum of an infinite series is equal to the first term divided by 1 minus r. So we've got to figure out the first term, and we've got to figure out r. So my first term is going to be when k is 3. So it's 8 times 1/2 to the 3 minus 1. So that's 8 times 1/2 to the 2. So that's 8 times a quarter, which is 2. So my first term is 2. And now I have to figure out my common ratio. Now, because this equation is ar to the n minus 1 and it's written as that, I know my r value is a half, but I could also solve for it if I found the second term and then divided the second term by the first term. But I know that my value is a half. So this is 2 divided by a half, which I know is 4. All right, moving on to the next example. All right, so this last example is an application, and it's an application of geometric series and infinite geometric series. So we've got a racquetball, which is being hit in the air 27 feet, rebounding to 2/3 of its previous height after each bounce. We want to find the total vertical distance, so that's a sum. The ball has traveled when it hits the ground the 10th time to the nearest foot. So this is not an infinite geometric series. This is just a finite or a partial geometric sum. So what we have to figure out is, what are we going to put in? Well, the equation is Sn equals A1, so first term, times 1 minus r to the n all over 1 minus r. So I have to know the first term, I have to know the common ratio, and I have to find the number of terms. And this one, it's not as easy as it sounds. So I actually like to draw it. I'm like, okay, so the first time the ball goes, it's going up 27 feet. Then what's going to happen is it's going to rebound. So it goes up 27 feet and it goes down 27 feet. Okay, and then when it comes back up, it's only going to rebound to 2/3 of its previous height. So 27, but only 2/3 of that. And then it's going to go up and down. And then the next time it goes up, it's going to go 27 times 2/3 twice. So 2/3 of the previous height. So 27 times 2/3 times 2/3, or 2/3 squared, and it's going to come back down. And then it's going to do it again. 27 times 2/3 to the 3, and so on. And we want to know what's going to happen by the time it hits the ground. So it's going to come up and down for the 10th time. So this is hitting the ground the first time, the second time, the third time. So first time, second time, third time, fourth time. So you can see sort of the pattern that when it hits the ground for the fourth time, it's rebounding 2/3 of the height 3 times. When it's hitting the ground for the third time, it's squared. So this one's going to be 27 times 2/3 to the 9. All right, so how are we going to use this information? Well, what's my first term? We want to know the total vertical distance the ball has traveled when it hits the ground the 10th time. So if I look at this one, what I'm looking at is that the vertical distance it hits for the first time is up and down. And so it's going to actually be 54. So 27 plus 27. So I'm going to put into my equation that the first term is that it's traveling 54. Some people do this for just the ups, and then they just times that distance by 2, or you can do it as up and down. It's sort of up to you. And then 1 minus, we know that the common ratio is 2/3, and we know that the number of terms is going to be 10. Right? So even though a 9th would go in here, we don't actually care because it's not arithmetic and we don't have to know that last term. We just want to know that the number of terms is going to be 10. And then over 1 minus 2/3. All right, and again, we have to do calculator work, but it tells us that we're going to the nearest foot, which means we don't have to figure it out in fractions and we can just plug this in. And so if you plug it in, you're going to do 54 times, or bracket, 1 minus 2/3, or 2 divided by 3 in brackets, whatever you do, to the exponent 10, unbracket, divided by bracket 1 minus 2 divided by 3 unbracket. So I get 159.1906 ... which means to the nearest foot would be 159 feet total. Okay, so then let's look at this next one. The next one says, find the total distance the ball has traveled by the time it stops bouncing. Means that we're talking about an infinite series. So we're going, the sum of an infinite series is equal to the first term divided by 1 minus r. Again, I'm going to use that first term as 54 feet up and down, and I'm still going to use the common ratio of 2/3. So it actually just becomes a way easier formula to plug in. So this is 54 divided by 1/3, or 54 times 3. Keep getting divided on my calculator. 54 times 3, which is going to give me 162 feet. So by the time it comes to a rest, it'll have traveled a total of 162 vertical feet. All right, go do your quick checks and good luck on your Chapter 11 test.